Hello, everybody, and welcome back. We are now in Chapter 14. Again, follow the syllabus for the chapters and content that we cover. We do start to jump around quite a bit from this point forward. In this week, we're going to discuss 3 chapters. So keep an eye out. There will be more content than we typically see. That's because the next 2 chapters after Chapter 14 are very short in content. After chapters 16 and 17, again, we jump. We're going to move on to off-book topics. So we'll be discussing things that aren't depicted the same way in the textbook that we will discuss them. I've made PowerPoint videos, and we're going to be following StatKey very strictly in these upcoming chapters. But for now, we're in Chapter 14. In my opinion, probably the most interesting chapter. We're going to be dealing with probability and long-term expectations, or expected value. Typically, in class, I would be asking everyone, does anybody here play poker? And then discuss how understanding probability will make you a better card player. We're going to just assume here that everybody does play poker. And if not, one thing that you should do is familiarize yourself at least with a basic deck of cards. So if you don't know what's inside of a basic deck of cards, how many suits that there are, how many colors that there are, and so on, pause the video and take out a deck of cards, or Google if you don't have one with you, and just refamiliarize yourself. Okay, let's get started. Our first thought question. 2 very different queries about probability. Our first, if you flip a coin and do so fairly, what is the probability that the coin will land heads up? So by doing so fairly, we're going to do so assuming that the coin is fair, meaning that both sides, heads and tails, are equally likely to occur. So if both sides are equally likely to occur, how would I find the probability that the coin lands on heads? Well, we'll be discussing that shortly. Query B. What is the probability that you will eventually own a home? That is, how likely is it that over the next 5 years we are going to purchase a home? Well, out of the 2, queries A and query B, I think query A is going to be very easy to calculate. How many possible outcomes are there when I flip a coin? 2. Heads or tails? What's the probability that the coin is going to land on heads? Well, one of the 2 outcomes are heads, and since the 2 outcomes are equally likely, we're going to later see that the probability that I flip a coin and it lands on heads is exactly 1/2. Is that going to be as easy to calculate for owning a home? Owning a home doesn't work the same way as a fair coin. The probability that I will own a home versus that I won't own a home aren't necessarily the same. Because of that, it's going to be much more difficult to calculate a probability like that. Our second thought question. Explain what it means for someone to say that their probability of owning a home is 70%. Well, first of all, we have to understand that 70% is saying 70 out of 100. So if I ask you the probability that someone will eventually own a home, what I'm saying is out of every 100 iterations, I'm expecting 70 of them in which you own the home, which would mean 30 of them that you don't. Now, do I think that this is going to be calculated the same way as we did with our fair coin? Right? 2 possible outcomes and they're equally likely? No. We're going to discuss how we have to calculate probabilities like this. On to thought question 3. It says, what's wrong with this partial answer to question 1? The probability that I will eventually own a home is 1/2 because it either will happen or it won't happen. Well, we kind of already touched on this, didn't we? The probability that somebody will own the home versus them not owning a home. They're not necessarily equal to each other. Yes, they're two outcomes, but both outcomes don't occur in the same frequency. This isn't a fair coin. Thought question 4. Why do you think insurance companies charge young men more than they do older men for automobile insurance? And why do they charge older men more for life insurance? Well, we are in the probability chapter. This has to do with probability, right? Younger males tend to get involved in more automobile accidents, have a higher rate in which they incur moving violations, and they're a larger risk to the insurance company. So that's why they have to pay a larger premium. Older men are more at risk, unfortunately, of needing life insurance. So that's why their insurance premiums for life insurance would be higher. It all has to do with the probability in which they'd actually need to use the service. Finally, thought question 5. How much would you be willing to pay for a ticket to a contest in which there was a 1% chance that you win $500 and a 99% chance that you win nothing? We're going to get into questions like this dealing with expected value. But the first question we have to ask is, are we going into this contest assuming that we're trying to win money? Right? There's only a 1% chance that I win $500. Would I pay $0? Sure, because there's no downside. How much money would I actually be willing to put forward on the chance that I win $500? Does it make sense that you would spend $100 for a 1% chance to make $500? Probably not. We're going to discuss expected value calculations at the end of this chapter. Probability. What does the word probability actually mean? Well, we're going to go through a couple examples. So, for the probability of winning a lottery based on buying a single ticket, we can quantify these chances exactly. How many total possible combinations are there to hit the jackpot? Well, the probability of winning the lottery would be 1 out of that total number of possible combinations. All of those numbers are equally likely to occur. Just like if I were to roll a die. If I were to roll a fair die, a 6-sided Monopoly board die, what is the probability that I'm going to roll an even number? Well, there's 6 values on the die. 3 of the 6 are even, so the probability that I'd roll an even would be 3 out of 6, or 1/2. We can find these values exactly. Now, if I were to say, what is the probability that I will eventually own a home? We're basing our assessments based on our own personal beliefs, making an educated guess. We call this subjective probability, where we can't quantify the exact value. So based on my experience, based on my educated guess, what do I feel that the probability will be? Calculating exact probabilities for things like rolling a die, flipping a coin, these are a little bit easier. Subjective probabilities, we have to explain why. Section 16.2, relative frequency interpretation. The relative frequency interpretation applies a situation that can be repeated over and over again. These situations, we can think of these out loud, right? Buying a weekly lottery ticket and observing whether we won. That's something we could do week after week. Commuting to work daily and observing whether a certain traffic light is red when we reach it. Testing individuals in a population and observing whether they carry a certain gene that's a disease marker. Observing births and noting whether the baby is male or female. These are all examples of things that we can repeat over and over again. And what we can do is we can actually find the probability based on these repeated, these repeated activities, these repeated experiments. So, before we move on, let's think about another example. Rolling a die. If I were to roll a die and then record the value, I roll a 4 the first time, I roll a 5 the second time. What I can eventually do is see that the probability of rolling a 4 is going to tend towards 1/6. I have a 1 out of 6 chance of rolling a 4. The probability of rolling a 3 will also trend towards 1/6. We call this the idea of the long run frequency, relative frequency. The probability is the proportion of the time it occurs over the long run. So if I were to flip a coin, and if I were to flip this coin once and I get heads, do I expect to get heads every time I flip the coin? No, of course not. What if I were to flip the coin 10 times? I have 6 heads and 4 tails. Do I think that the probability of flipping this fair coin and getting heads is actually 6/10? No. It's because one experiment or a small number of experiments aren't enough to give me this long run relative frequency. We need to calculate this out with multiple experiments. We have to do multiple iterations here. If I were to flip this coin infinitely, we would see that the probability of getting a heads would be that 1/2. So let's look at the example we have here. So it says the long run frequency of males being born in the United States is about 0.512. So what we did was we just had an observational study. Why couldn't this be an experimental study? Well, you can't force somebody to be born a male. You can't force somebody to be born a female. So we're just observing and reporting. So after 1 week, there were 30 babies born. 12 of them were male. After 2 weeks, 100 babies born. 47 were male. So after these 4 weeks, about 47% of the babies born at this particular hospital were male. But over the long run, as the weeks increased further and further, until I get to 52, when I look at that 1 year, 1,200 babies being born, 618 of them being male. 0.515. This is trending closer and closer to our long run relative frequency. Over the long run, we expect about 51% of the babies to be male. We didn't see that after 1 week. We didn't see that after 4 weeks. After the long run, we would see that trend. Determining the probability of an outcome. Now, we've already discussed our classical probability approach. Right? Assuming that I have a fair coin, assuming that I have a fair die, we can calculate the probability. So let's do one out loud. Assuming that I have a fair coin, what's the probability that the probability that the coin will land on heads? 1 out of 2, right? 2 possible outcomes and they're both equally likely. How about a fair die? Assuming that I roll a fair die, what's the probability that I'll roll a number higher than 4? Well, how many outcomes are higher than 4 on the die? 5 and 6. There's 2 outcomes higher than 4. There's 6 total outcomes. So the probability that I would roll a number higher than 4 would be 2 out of 6, or 1/3. 1/3 of the time I expect to roll something higher than a 4. Method 2, observe the relative frequency, or the empirical probability. We can't always assume that all outcomes are equally likely. So here we're doing some type of experiment, and we're just simply recording the results, just like we had here. This is a perfect example of an empirical probability. In the long run, after 1,200 experiments, 1,200 children being born, approximately 51% of the children were male. Okay. Now, for this relative frequency interpretation, it says it can be applied in situations where the experiment can be repeated over and over again. If I need this to work in the long run, I need to be able to do the experiment multiple times. It says the relative frequency should settle down to that constant value over the long run. I'm going to approach the true probability. Now, this is important. It says this does not apply to situations where the outcome is influenced by the outcome of the previous experiment. So let's take this example. Let's say that I have my deck of cards, and I did ask everybody to familiarize yourself with a deck of cards. I have 52 cards in my deck. There's 4 suits: hearts, diamonds, clubs, and spades. And they're all equally represented, meaning that I have 13 clubs, 13 diamonds, 13 hearts, and 13 spades. If I were to draw a card, what's the probability that I get a diamond? Well, there's 13 diamonds out of 52 cards, 13 out of 52, or 1/4. Now, if I were to draw another card, what's the probability that I get a diamond again? Well, that's going to change things. It all depends on what I did with the first card. If I put that first card back into the deck, I still have 52 cards, and I still have 13 diamonds. Meaning that I still have a 13 out of 52 or 1/4 chance of drawing a diamond. But if I didn't take that card and put it back into the deck, if I left it off to the side, now I only have 51 cards in the deck. And only 12 of them are diamonds. So what's the probability that I drew another diamond? Well, that probability would have been what? 12 out of 51. So we have to understand whether the experiment can be repeated over and over. Now, this is very important. This relative frequency interpretation cannot be used to determine the outcome of just one experiment. If I said that I have a fair die, and I said, what's the probability that I'll roll something higher than a 1? Well, 5 of the 6 sides are higher than a 1, so I'd have a 5/6 chance. That's the most likely outcome, higher than a 1. But that doesn't mean that I'm not going to roll ones. I'm going to roll a 1 1/6 of the time. I can't use this relative frequency interpretation to determine just the single outcome. Person probability. So the personal probability interpretation. This is our subjective probability. The person probability is the degree to which an individual believes that an event will happen. It says that these probabilities must be between 0 and 1, as all probabilities must be. 0 would be a 0% chance. 1 would be a 100% chance. We can't have a probability that's less than 0, less than a 0% chance. And we also cannot have a probability that's greater than 1. Something can't be more than 100% likely to happen. So all probabilities have to be between 0 and 1. And they also must be coherent. What that means is that our personal probability for one event doesn't contradict our personal probability for another event. So let me give an example of something that would not be coherent. I believe that there's a 60% chance that the Yankees will win the World Series. And I also believe that there's a 50% chance that the Phillies will win the World Series. You can see that together they add up to over 100%. So that's not coherent. All right. So personal probabilities. Let's look at an example. The probability of finding a parking spot downtown on a Saturday. Based on my educated guess, based on my experiences, what do I feel that that probability will be? The probability that a particular candidate will be the best position, or sorry, will be the best candidate for some particular position. The example that I always used to use, and unfortunately it doesn't work quite as well anymore, was the probability that the Philadelphia Eagles will ever win the Super Bowl. I always used to say that was very small. Now I like to say the probability that they'll win the Super Bowl again will be very small. Let's apply some simple probability rules. Now, we have the actual formulas at the very end of this video, and I'll briefly show them to you, but they're not formulas that I would like you to memorize. I want you to understand it. If we understand the concepts, we don't have to memorize the formulas here. So, rule 1. If there are two possible outcomes in an uncertain situation, their probabilities must add to 1. If I have two possibilities, one of the two has to occur. Either event A happened or event A did not happen. Those are the only two outcomes. So together their probabilities must add to 1 or 100%. If I know that, I can work backwards to find unknown probabilities. So if we said the probability of a single birth resulting in a male is 51%, then by working backwards, 1 minus that 0.51, the probability of a single birth resulting in a female would be 49%. Now, be careful here when I say two outcomes. If I were to say, what's the probability on a fair die that I roll a 5? Well, rolling a 5 would be what, 1 out of 6? What would be the alternative to rolling a 5? That would be not rolling a 5. The probability that I would not roll a 5, meaning any number other than 5, 1, 2, 3, 4, 6, would be what, 5/6? Together, the probability of rolling a 5 and of not rolling a 5 would add to 1, 6/6. Addition rule. It says if two outcomes cannot happen simultaneously, then they're said to be mutually exclusive. If I have two mutually exclusive events, the probability of one or the other of the two events occurring is simply the sum of their individual probabilities. Let's start by discussing mutually exclusive first. If I roll my die, can I roll both a 4 and a 5 at the same time? No, of course not. The die is either going to have one number or the other number. But can I roll my die and roll either a 4 or an even at the same time? Sure. Right. Those would not be mutually exclusive. They could occur at the same time. So if the events are mutually exclusive, the probability of one or the other occurring is simply their sum. Let's look at our example. If I believe my personal probability that there's a 50% chance that I will get an A in my statistics class and a 30% chance that I will get a B in my statistics class, that means that the probability of getting either an A or a B is simply the sum of the probability of A plus the probability of B. 30 plus the 50 gives me the 80%. Now if I work backwards, what's the probability that I get a C or less? Well, I'm either going to get an A or a B or a C or less. There's two possible outcomes. 1 minus 80% would give me 20%. Okay. If two events do not influence each other, i.e., if the knowledge about one event does not help the knowledge of the probability of the other, these events are said to be independent. If two events are independent, then the probability that both will happen is found just by multiplying their probabilities together. Is flipping a coin independent? If I were to flip a coin and get heads, does that influence the next coin flip? No, it doesn't, right? If I were to roll a die and get a 5, does that influence what I get on the next roll? Of course not. If I were to pick a card from the deck and I get the King of Spades, does that influence what I would get on the next card? That depends on what I do with the card. Remember, if I put that card back in the deck, I still have all 52 cards, and that King of Spades is still one of the 52. But if I keep that King of Spades off to the side, now I have a different number of cards and I'm missing the King of Spades. So that probability would be changed. That would be a dependent event. Let's look at our example. Women, a woman will have 2 children. It says, assume the outcome of the second birth is independent to the outcome of the first. And that the probability of getting a boy is 0.51, which we had showed previously. So it says, what's the probability that we have a boy first, followed by a girl? Well, what's the probability of getting a boy first? 51%, 0.51. Multiplied by, again, we're assuming independence, the probability of getting a girl, we already showed was 49%. So it's simply the product of the two. And this makes sense. It's approximately a 25% chance that you'll have a boy followed by a girl. Rule 4. If the ways in which one event can occur are subsets of those in which the other event can occur, then the probability of the subset cannot be higher than the probability for the one in which it is a subset. Now this is really intuitive. The definition is a little wordy. So I made a Venn diagram that we'll see in just a moment. It says, suppose you're 18 and speculating about your future. You decide the probability you will eventually get married, important here, and have kids is 75%. So the probability that both of these occur is 75%. What Rule 4 is saying is that the probability of having kids has to be at least 75%. The probability of getting married has to be at least 75% if the intersection of the two is 75%. Let's look at our Venn diagram. In my first circle, I have the probability of getting married. In the second, I have the probability of having children. What we're saying is that this intersection is 75%. The entire circle for the probability of getting married has to be at least 75%. Same thing of having children has to be at least 75% if the intersection is 75%. That's what we're saying here with Rule 4. When will it happen? The probability an outcome will occur on any given instance P. And the probability that the event will not occur would be 1 minus P. Again, that's Rule 1. We call that value Q. So P is the probability the event occurs, Q is the probability that it does not. If these events are all independent from each other, let's look through our formula. What's the probability that my event occurs on the first try? Well, that first try would be what? P. What's the probability that my event occurs for the first time again on the second attempt? Well, that means on the first attempt it was not P. So this 1 minus P could also be written as Q. Q times P. Okay. Now I'm on my third attempt. Say this event has not occurred yet. What's the probability that the event will occur for the first time on my third attempt? Well, this would be what? Q didn't occur the first time. Q, it did not occur the second time. P, it occurred the third time. And so on. We get to see this pattern. Now, an example of a question like this would be rolling a die until I roll a 1. What's the probability I roll a 1 on my first try? 1/6. Well, if I didn't roll a 1 on the first try, what's the probability I do it for the first time on my second? Well, that means that the first try was not a 1, right? So that would be 5/6 multiplied by my 1/6 because I did roll a 1 on the second try, and so on. Let's look at an example. The probability of a birth resulting in a boy, again, is 51%. It says, suppose a couple will continue to have children until they have a girl, and that births are independent of each other. What's the probability that they'll have a girl on their very first try? Well, 49%. If they don't have a girl on the first try, they're going to try again, which means that the first try was not a girl, was Q, right? 0.51. And then on their second attempt, if they had a girl, they would stop. And there's approximately a 25% chance that occurred. And if they continue in this pattern on the third attempt, if they did not have a girl until their third child, they had a boy, then they had a boy, and then finally a girl. If I go all the way down to the seventh attempt, that would mean that the first 6 children were all boys. So this will be what? 0.51 to the 6th multiplied by 0.49. There's less than a 1% chance, right, that this would occur? This is an additional example. So it says, suppose the probability of being infected with HIV is 1 in 500, which means that the probability of not being infected, again, by rule 1, would be 1 minus that value, 0.998. So what's the probability that you're infected on the very first attempt, the first encounter? Well, that's the 1 in 500. 2,000ths. Well, if I didn't get infected on the first attempt, what's the probability that I got infected on the second? Well, that means I did not get it the first time, 0.998, multiplied again by I did get it on the second, 2,000ths. Well, we can continue in this pattern for any number of encounters. All right. Long-term gains, losses, and expectations. This is our expected value. It says, all customers are charged $500 a year at this insurance company. 10% of them submit a claim in any given year. And the claim always awards $1,500. How much will the company expect to make per customer? Well, let's remember that they're bringing in $500 per customer. So 10% of the time, they're going to have a loss of $1,000. 10% of the time, they'll lose $1,000. Again, it's 1,000 because they already brought in 500 from that customer. If only 10% submit claims, that means that 90% do not submit claims. So 90% of their customers actually net them $500 in profit. So let's go to our formula. The formula for expected value is the amount multiplied by its associated probability, and it's the sum of these values. So what's the amount gained if somebody filed a claim? Well, they actually lost $1,000. I'd multiply that by its associated probability of 0.10. If somebody did not file a claim, they gained $500, the associated probability being 90%. So Let's clarify this here. This is 90% of the time they gain $500, 10% of the time they lose $1,000. It's the sum of these two values. What does that mean? That means on average, the insurance company is making $350 per customer. Does any single customer give them $350? No. Right? Customers in this case will either give them $500 or make them lose $1,000. But what we're saying is, on average, the average of these values is that the customer nets them a $350 profit. Okay. Let's look at another example. A lab orders a shipment of 100 rats per week, 52 weeks a year, from a rat supplier for different experiments. The prices for the weekly shipments follow the following distribution. Based on their supply and demand, the prices change. So 45% of the time, it's $10 for the 100 lab rats. 20% of the time, it's $12.50. And 35% of the time, it's $15. If the lab is trying to budget how much money that they need for the lab rats in any given year, well, let's see. For 1 week, 45% of the time it was $10. I'd multiply the probability by the associated amount. 20% of the time it was $12.50. Again, multiply the probability by the associated amount. And finally, 35% by the 15. And again, the expected value is finding the sum of these products, the probability by their associated amount. What we're saying is, on average, an average week would be $12.25. Notice again that none of the weeks were $12.25, but my average week will be $12.25. So now if I said, well, how much should we budget in order to make sure that we have enough for any year? Well, I take the average of 1 week and just multiply by the number of weeks. The budget should be $637 based on our averages. So our expected value, let's go ahead just a second, is the theoretical average. That's what this stands for. Expected value is the theoretical average. Let's look at a lottery game, and let's be smart. Nobody plays the lottery assuming that they're going to win. So if I spend $1 to play the lottery, do I expect to actually gain money on average or lose money on average? I should be losing money, right? Let's look at this particular lottery. The probability that you match none of your given values is just under 73%. If I match none of the values, I lose the dollar that I spent in order to play the game. The probability that I match just one single number is just about 24%. And it says here that the prize is a free ticket, which means that the dollar that it cost me to play the game, I got back. I didn't make money, I didn't lose money. Net gain of 0. Now again, we're not expecting to make money on average here, right? Just out of these two, the 0.242 and the 0.726, that's over 90%, well over 90%, which means that less than 10% of the time we're actually going to make money. If I match two of the numbers, I make $4 in profit. Again, subtracting the $1 I paid to play. Match 3, I make a $49 profit. But if I match all four, $5,000 prize, I have a profit of $4,999. So let's find our expected value. I multiply the amount, again, where we subtracted each of these minus the $1 it cost us to play, multiplied by the associated probability. Multiply the amount by the probability for each of these. You can see here that we didn't even bother multiplying 0 by this probability. We knew that would be 0. And then we find the sum of these values. So what is this saying? On average, every time I play the lottery, I'm expecting to lose 35 cents. For every $1 I put back in, I'm expecting about 65 cents back out. All right. Let's look at our next example. It says, suppose 40% of the people in a population smoke a pack of cigarettes or 20 cigarettes a day, which means that 60% will smoke none. Those are our only two conditions. Either you smoked a full pack or you didn't smoke at all. If I were to find the average of any person, how many cigarettes that they smoked per day? Well, 40% of the people smoke 20 and 60% of the people smoke 0. So what we could say is that the average person smoked 8 cigarettes. But again, we don't expect any individual to smoke 8. They either smoked 0 or they smoked 20. So we call this the expected value, but it is important to remember that that does not mean I'm actually expecting one of these outcomes to occur. It's just my theoretical average. As always, I do like to show you the formulas. These are in the textbook. We're not memorizing our formulas. If you were to take a traditional stat course, this would be something you'd spend hours memorizing. Okay. So that brings us to the end of our slideshow. Again, this is the slideshow for chapter 14, Understanding Long-Term Probabilities. We are going to get into our upcoming chapters shortly. If you have any questions, please reach out to me. The new homework will be posted on WebAssign. If you have questions, just let me know. Thank you.